Okay, welcome back everyone. In this video we're going to be looking at forces and talking about the basic definition and also the types of forces that we will be talking about and how to add forces using vectors. So we're going to start with a pretty basic definition of a force. A force is just nothing more than a push or a pull. And what it does is it produces a change in motion. So what we really mean by that is that a force produces a changing velocity. And of course, if you divide that by time, you're going to produce an acceleration. And these are vectors. So the change in velocity and the acceleration is a vector because so is a force. So we should talk about the magnitude and direction of a force vector. The magnitude is just how much force you have measured in newtons, and then the direction is usually an angle. I'll give you an example of that in a moment. So remember that newtons are actually made up of kilograms times meters per second squared. So that's sort of the definition of what a newton is. Okay, so let's talk about how to add forces. And as we've said in a previous video on projectiles, there are different ways to add vectors. One way is what we call the parallelogram rule. And so what that means is that if you have two vectors, maybe one going up and one going over, is that you make a little parallelogram with little dotted lines. And to find the total of those two vectors, or the resultant, you draw in the diagonal. So if I had another scenario where I had one going like this and another one going like so, again I would draw in my little dotted lines and draw in the diagonal. Okay, and these are what we call the resultant, which is what you get by adding two or more vectors. So that's the parallelogram rule, and that can be useful, but I think that it's much better to always use what we call head to tail. And in head to tail, you take your two vectors and you draw them so that the tail of the second vector is lined up with the head of the first. So if I have a vector A and B, vector B has its tail touching the head of vector A. And so then what I do is I draw my resultant from the first tail to the last head. Okay? So again, that's the resultant. My other example of this would be head to tail going like so, and then over like this. And again, my resultant would be from the very beginning to the last head. And notice that I get the same answer as using the parallelogram rule, but the good thing about using head to tail method is if you have several vectors that you need to add at the same time. For example, let's say you have an object, it's sitting on a table and it has 1, 2, 3, 4 forces acting on it. And it doesn't matter what the numbers are, we can fiddle with that later, but for now we just want to calculate or draw rather, the total force. So I would do the same thing. I would draw 1, and from the start of that, or from the end of that, I would draw the next one. So if this is vector A and B and C and D, this would be vector A and B, and then C would go about like this, and then D would go something like this. And so we start at the very beginning and we go to the very end, and that would be vector r, the resultant. So this is why head-to-tail method is easier to use than parallelogram. Parallelogram, you have to keep making more parallelograms for every additional force vector that you have. So now how about a concrete example of how to add force vectors? And so if I have vector A, which has a value of about 10 newtons, and vector B, which we'll put head to tail, with a value of about 7 newtons, what would be the total force or the resultant from adding those together? So again, I start at the very beginning and I go to the end, and that resultant would depend on whether or not this was a right angle. Right now it's a right angle, so I can use Pythagorean theorem to say that it's the square root of 149 newtons, which is about 12.2. So that's 10 squared plus 7 squared, and take the square root. But then the other thing I can do is I can describe an angle for this, and there's many ways to describe the angle. One way is to say that the tangent of this angle is 7 over 10, and that's newtons, but they cancel out. And if you take the inverse tangent of each side to solve for the angle, I didn't really write that very neatly, but the inverse tangent of 7 over 10 gives you an angle of about 35 degrees. But we have to say where this is. We could say that this is 35 degrees east of north. And so north is kind of going in the direction of A. Okay, so this is north. East is going that a ways. And so if I'm going over 35 degrees, it's east of north. Now, of course, most of the time in math class, we just draw the x-axis and we draw the angle from the positive x-axis. So another way I could write this is that it's simply at 55 degrees. And then people would understand, oh, it's from the positive x. Okay, so now let's talk for just a moment about what we call the net force. So the net force, now that we know how to add vectors, the net force is what we say is the vector sum of all the forces acting on a particular object. And we might also talk about the net force acting on a system, but we'll talk about that more in a later video. So the way that we write net force is F with a vector, net. Okay, another way that you sometimes see this written is the summation symbol. So that literally means sum of, so sum of the forces. And then another way you might see this done, but only sometimes in my class, is you might see a little grid like this. And of course this is a net, and there's the net force. Get it? Okay. Alright. Alright, so the final thing to talk about for this video, that was an email, are the two types of forces, because we can broadly categorize forces into two types. And they are contact forces and non-contact. So let's just list some of the forces and describe what category they fall into. So first of all, there's weight, which is the force of gravity acting on an object. And we'll be talking about many of these later. There's tension, which is a force that exists in ropes and chains and strings. And then there is a given force. So in other words, someone's just pushing or pulling with a certain amount. Then we could have a normal force, and that name comes from the fact that it is a perpendicular force to a surface because of contact. Oh, I guess we kind of gave that one away. A normal force is a contact force. So a normal force is a perpendicular to a surface because of contact between two objects. So if I have a surface here and a book here, there could be a normal force, F normal, pointing sort of outwards away from, if this is a wall and this is a book, the wall would be exerting a force outwards. And then we could have friction, and we could have things like a magnetic force or an electric force, and so on and so forth. Okay, so contact forces are exactly what they seem. They are when two things are touching, and so contact forces include tension, a given force, which is just the push or pull, normal force, and friction, which comes because of contact between two surfaces. Okay, so if this book was sliding down the wall, as we'll learn later, the force of friction would point upwards. So we'll get to that a little bit later. The other three are non-contact forces, because if I drop an object, the force of gravity acts without two things actually touching. The magnetic force is a non-contact force, and the electric force is a non-contact force. These are sometimes called field forces, and we'll be talking a lot more about fields in later videos. And we sometimes call these action at a distance forces. And actually, Newton was kind of stumped. He figured out what gravity was, or rather how to describe it mathematically, but he couldn't really explain it. He thought that maybe the Earth went around the Sun because of a gigantic string, but he wasn't really sure. So we'll be talking more about action at a distance forces in a later video.